that you are going to apply the force F2 over here. So for this nut to rotate, this will do a torque like that. So this one will have to do a torque in this direction for this one not to move, and of course F2 will have to be greater than F1, and for the whole thing not to move, then the force that is going to show up here on the pivot, it will have to be pointing in this direction because this is greater than that. So the answer is that one over there. In this particular case, this one goes like that, this one's going like, no matter what you do here, this is going to rotate. The same is here. There is no force that you can apply here to prevent this from rotate. But in here, if you apply a force, that it will balance these two because this prevents this, this torque cancels, so this doesn't rotate. So in here, you could do that. In this particular case, you have a plank that is 6 meters long and weight 800 newtons. So in the center, of course, you can balance it. Now, if you want to add 160 newtons over here, so this is 80 newtons. If you want to, then you will have to move this in a way that the you will have to move it to the right, so the 80 newtons will be here, and the 160 newtons will be here, and this distance here will be twice this distance. So you will have to move it to the right 2 meters. This is a very similar problem. You have a stick that weighs 240 grams, so the mg is 240 grams, and you want to put 240 grams over here. So in order to balance it, then you will have to put the thing here. So if this is the 100 centimeter mark, that is going to be the 75 centimeters mark. The reason why this doesn't slip is because the coefficient of friction between the ladder and the floor must not be 0. This one, if you want to calculate this force, then this force, since this is 5 meters, this is 4 meters, so the torque around this point of this force is F times 4. And that has to be equal to the torque due to the weight, which is 800 newton times 1.5. So this force is 300 newtons. In this particular case, the tension here balanced this way. Here the tensions are equal. In this particular case, the tension in A is greater than the tension in B, because this is closer in order to balance the torque, and in this case the tension B is greater than the tension A. So from least to greatest is 213. This one, if the linear acceleration, of course, is alpha times r, so that gives you 3 meters per second square. And then the distance is nothing more than 1.5 a times the time squared. So if you do that, you get 13.5 meters. This one is when you have the wheel here, and you push with a force F here, and then it's rolling, and then the force, the friction is like that. Then F minus F has to be equal to ma. But also the torque, the only torque that is done is done by the friction force, which is equal to the moment of inertia times the angular acceleration, which is A divided by R. From here you get that the friction force is ma over 2. So if you go back here, then the big F is 3ma over 2. It's a bit tricky, but that's the answer. When you have two uniform cylinders and they have different masses and they have different rotational inertias, and which one gets there first, then they arrive together. Because actually what you did is, when you have this is the way you reason. You say mgh is equal to, it's all kinetic down there, m1v squared plus 1.5 I, and omega squared, remember, is always v squared over r squared. So the because the rotational inertia is going to be that of a cylinder, which is going to be 1.5 mr squared, all the m's are going to cancel and the radius are going to cancel. So the velocity is not going to depend on that. This is just 100 revolutions is 2 pi times 100 radians. So you divide that by 10 seconds and then you get this over here. After 6 seconds it's minus 24, so it's minus 24, then it's 36 at the beginning, and then this has to do with the time, which is 6 seconds. So this is going to give you an alpha of 2 radians per second squared. So that's going to be that. This one, the masses that contribute to rotate are this one, and this one. So if they are all identical, these contribute with ma squared, because this is the important distance. These contribute with the same plus ma squared, and this, the distance is 2, so this is 4 ma squared. So this is 6 ma squared, so you do that, you get 12. The in this particular case, all the forces are the same, and you want to calculate the torque that they produce. So F2 produce no torque, F5 produce no torque, so they produce a torque of 5, so they have this lowest magnitude. Then F1 and F3 produce the same torque because they are the same distance, and is greater than the one produced by 4, because the one produced by 4 is only by this component, which is less than that. So that's the answer. The so let me just make sure that I didn't jump. No, it's fine. Now you have this one. Then the it, of course, it pulls in both blocks, but exerts a heavier force on the greater block because this has to rotate. So this torque on the heavier block has to be greater than the torque on this one in order to rotate in that direction. This is where the heavier block is going down. The this is just simply a number. You take the 1.5 for the mass 2 is 2 squared, for the mass 4 is 2 squared, and for this one is 4.5 10 to the minus 3, and then the velocity is 2 squared divided by the radius squared, which is 9 10 to the minus 4. You do all of that and you will get 22 joules. The in a liquid, the pressure, of course, is the same at all points at the same level. Here, the pressure difference between this point and this point is rho GL, and it's equal to the pressure difference between this point and this point, which is the force of divided by the area. So the answer to that is this one over here. Finally, you displace more fluid if there is less density. So from least to great is that. And this one, we know that it remains the same. And in this case, because the pellet is more dense, it's probably lower. And this is a factor of 100. A factor of 16 on the area, so the factor is 16. So it's going to be like that. So